Okay. Here we are. So, dear students of probabilistic robotics, this lesson is being recorded as a replacement of the recording of the first part of the lesson we had yesterday, which was on bias filtering. So, while manipulating the lectures, I realized that the audio quality was too often interrupted, and I would like to give you some proper material where you can follow basically the lesson, especially for the remote students. So this will, in case you understood the previous recording, then there's nothing you have to do. If you have some doubt or the brittle connection or the problems that we had in streaming last time affected you, then or hindered your understanding, then this video here for that stream. Okay, so what we will be talking about is the implant of filtering on which we will basically construct all other filters that we will encounter in the during the course. The audio quality might be excellent because this is a gift from a dear friend, Celestaknis, that well, basically sponsored me with a new microphone. So I think that the audio quality is more than decent. And then we start our lesson. Was aim is to frame the bias filtering in two different ways, in two different following two different derivations, one which is the classical one, and the other one is the derivation which is based only on basic probability operations, which are the usual one, marginalization, conditioning, and so on, that you should be familiar with. So, here we go. 5. Very good. So, filtering is the kind of inferences in a dynamic Bayesian network, which is, I recall, a way to representing the probabilistic evolution of a dynamic discrete system. Is that particular inference that asks to determine the state distribution at time t, knowing all the previous controls and all the previous observations. So these previous controls and these previous observations are on the right hand of the conditioning bar, so we should assume, or we have to assume in this inference problem, that they are known. And this is typically the case in many problems, because you can, in many robotics problem, because you can, you know the control you issue to your actuators, and at the same time you're able to read the observations that come from the sensors. In addition to this, for instantiating filter, we need to know basically the system model, the probabilistic system model, which is which consists of the transition function, the transition model, which is the equivalent of the deterministic transition function in the deterministic case, which tell us the distribution over the next state by knowing the previous state and the previous control. So we can picture it as a distribution over the possible state at time t, which is controlled by two knobs, which is one is the previous state and the other knob is the previous control. The other aspect that we need to know is the probability distribution over the possible measurements that we could perform at time t by knowing, once again, that the state we are in this case, x of t. So again, x of t is a kind of knob that changes the shape of the distribution on the observations. In addition to that, we might assume to know, or we might introduce the concept of belief. The belief is the idea of the probability distribution of our filter, which will then become a recursive algorithm, so an algorithm that can be carried on incrementally as new measurements and new controls become available. We have to think about the distribution of the current state. In this case, bxt minus 1 means the belief at time t minus 1, or which is a distribution of the state that we think it is correct at time xt minus 1. In a normal functioning of the filter, you have an initial belief, which is the initial probability of your state that you can throw it in. In some filters, this probability can also be uniform. And as the filter evolves, this distribution will converge towards the estimate of a probability distribution over states that better represents the true distribution over the states of the filter. Remember that we are always estimating, we never know it for certain. We can only know the quantities up to a certain bound. All right, so our task will be then to develop this equation in a way that it can be rewritten by using these terms, which is the observations, the controls, the transition model, the observation model, and also we might think about implementing the filter only for one step, because the subsequent step will be exactly the same as the previous one, only that the variables and the measurements and the controls and the belief will be changing. To start our journey, we start from the target distribution, which is x of t given the previous states and the previous measurements. The first action that we can do is to basically extract from this list of measurements the measurement at time t. So then the list will become z between 1 and t minus 1, and zt will be alone. Again, remember that this is a conjunction of events, basically conjunctions of facts, and the conjunction, so the end, doesn't change its meaning if you just like swap the terms. So we can easily take z of t and shuffle it before. And we end up writing the equation number 2. Then, if you go back to the previous 2 lectures ago, the one where we recapped the probability, you might remember that we introduced the conditional bias rule. So the bias rule that includes an additional term, this term C, on the right hand of all members of the equation. And well, then we can proceed by identifying within this equation over here what is A, B, and C. By doing the assignment that A, in this case, is like quite obvious, because A is whatever stays to the left of the conditioning bar, is the current state, so what we want to estimate. Z of t will be the element that we just like extracted from the list of possible observations, and so having identified A and B, anything else is C. So having given this assignment to the set of variables that compose the formula, a straightforward application of the definition will lead us to the expansion, which is in equation 3. All right, and well, where we can identify p of z of t given the current state and all the rest, multiplied by p of x of t given all measurements up to all controls up to time t minus 1 and all measurements up to time t minus 1, and a certain number, another equation on the bottom, which is not function of z of t. Okay. All right. So another aspect that we can observe. We can focus actually on the denominator, which is the bottom side of the equation. The denominator, as I said, does not include x of t, so it doesn't depend on x of t. And so, being x of t, what we want to estimate, right, and being x of t not present in this formula over here, we can assume that x of t does not influence this value, which you should remember is just a number. So being just a number, we could replace it with a constant, which we will call eta, And given that we do not like to carry on fractions in our derivation, we will assign to eta the value of 1 over p of z of t given all the controls and all the measurements. Now, we could rewrite the equation before as equation 5, where this eta takes the role of the denominator, and then we have two terms. A term which is a probability distribution over the possible measurement, and another term which is the probability distribution over the possible states, all with the related conditioners. But then, focusing on this distribution, we can insert some, or we can highlight some independence assumption. And in particular, the independence assumption that arise from checking on the dynamic Bayesian network the meaning of this distribution. Using our color coding, where we have this purplish thing for the known distributions and this pinkish color for the query distributions, we figure out that by painting basically purple all the variables in the conditioner and by painting pink all the variables in the query, which is whatever stays to the left of the conditioning bar, we observe this pattern in the Bayesian network. And in particular, by looking at this pattern, we see that x of t is the only variable, the only way, whose knowledge absorbs all the knowledge of the past, basically, because that's the only way to reach z of t is through x of t. But if we know x of t, then we could basically say that all this other information contained in the previous control and in the previous measurements is irrelevant, because x of t is so much informative that will allow us to predict perfectly the distribution of z of t, and it will be the same as the one obtained by including these other terms. And so this basically means that this probability over here is identical to the probability of z of t given x of t, which is, by the way, our observation model, which expresses the likelihood of a specific observation given the state. Okay? And so, and this is already nice because we basically highlighted the presence of one of the initial ingredients in our final filtering equation. And so we rewrite the equation in this way. This is what we want to have. This is the famous eta. This is the observation model. And this is another probability. And this, at this point, we think it would be nice if we would be able to compute this probability. And we reason by wishful thinking. So first of all, we picture what this probability means, and then we figure out whether by knowing something more, we could easily compute this probability. And so, by painting basically this distribution over here in the Bayesian network, we would basically color with the previous color coding all the controls up to time t minus 1 and all the measurements up to the time t minus 1. We would not color xt minus 1. This we would not assume it known, right? Because it doesn't appear in this list. However, we observe that if we would know this probability distribution, then we would have a quite easy life, because in this case we could easily predict the distribution x of t just by knowing ut minus 1 and xt minus 1, which will then basically absorb anything about the previous time. Okay, so what can we do? Well, again, we check in our rulebook of probability identities if there is something that might help us. If we would know xt minus 1, which we don't, then we could easily write down basically that this identity, P of x of t given t minus 1 and all the controls and all the measurements, which will be equal to something we have in our ingredient list, which is the transition model. Again, we do not have this xt minus 1. So we look back in our rule book, as I said, and we observe that there are two nice rules that come handy to this purpose. The first rule is the conditional chain rule that you identify here, where you have that basically tells you that if you have a conditional distribution over A that depends on two variables B and C, and another in a distribution of B given C, then you could obtain the joint distribution still conditioned over C by multiplying the two. And then we have the always handy rule of marginalization that tells you that if you want to kick out a variable, in this case B, from a joint distribution, you just have to sum up over all possible values of that variable. In this case, you obtain P of A from P of A and B. The C is correct because it occurs in every term of this identity. If we combine this and this, it's not a surprise that we can directly obtain P of A given C, which is equal to the marginalization of the joint distribution that then is expanded through the chain rule. So having this equation at hand, we go back to our unknown distribution and we start, we try to identify, so to say, the elements. And in this case, the identification is quite easy because A is whatever is on the left of the bar and C is whatever is on the right of the bar. Having done this identification, well, then there is this magic term B that we have the faculty to insert. And in this case, which term B will we insert? We will insert xt minus 1 because we know that by inserting xt minus 1, we end up having that this part of the equation is equivalent to the transition model that we already have. And so we replace this equation over here by this summation in the bottom. Okay? And then we could rewrite that this is equal to the product over possible previous state of the transition model multiplied by another probability distribution over the previous state, conditioned to all the previous measurements and all the previous controls. Yet, and then with this identity, we once again rewrite the entire equation of the filter, right? Just to remember what we want to have at the very end. And what is the meaning of this term? This is basically the previous state given whatever I know up to the previous instant, including the previous control. Now we observe that if this term here would contain the control between 0 and t minus 2, then we could say that this probability distribution is just the estimated probability distribution at the previous instant, because it takes exactly the form of this equation over here, which is the belief at the instant t, and basically by subtracting from t, substituting t with t minus 1 everywhere here, you would end up with this equation, only that here you would have u between 0 and t minus 2, right? Because this is t minus 1 makes minus 2. If it would be the case, we would be enormously happy, because we would say, okay, you know, all what you need to know for estimating the distribution at the time t is basically the distribution at the time t minus 1 obtained through filtering, and the transition model, the observation model, and of course the controls and the observations, which are the input of your running engine. At the same time, if we paint this distribution, which at a certain point we will, or just like go here, if we paint this distribution, we would have that it would look like something something like this distribution over here. So let me go back. If we paint the distribution, this is xt minus 1 given u between 0 and t minus 1 and z1 and t minus 1. Now, it would look like something the like, where I have all these balls highlighted, also this measurement will be highlighted, this part is ignored, and then the pink part will be this xt minus 1. Please ignore this block over here, which is not present in this equation. So the query variable will be xt minus 1. Please, I repeat, ignore xt and zt, which are not present in the diagram. Then we figure out that this ut minus 1 is dangling there because we do not have xt in that equation. So what do we do with dangling variable? We just ignore them because they don't tell us anything, given that there is no connection with the remaining part of the inference. So recall again that in this equation we don't have neither xt nor zt. So if you want to visualize the diagram, you just ignore, you cut off from the diagram that part. And by visualizing the diagram, you figure out that even if you know u at time t minus 1 is completely irrelevant. So you could basically write p of xt minus 1 given all these parts, so u between 0 and t minus 1 and z between 1 and t minus 1 is perfectly identical to whom you can tell at that point to xt minus 1 given u between 0 and t minus 2 and z between 1 and t minus 1. And which is exactly what I've written here. And then now we are ready to do a wrap up, and then we identify equations which are the same up to an offsetting of an index, which is actually our belief. And we could express a way to compute the belief at time t, which is this one, starting from the belief at time t minus 1 and all the ingredients that I was mentioning beforehand. Okay? And this derivation here is the standard. This is the classical derivation, which is done in case of discrete events, because clearly it includes these summation terms. In case of continuous event, you could basically replace the summation with an integral. But the final formula will be then more an algebraic formula than something expressed in a probabilistic language with the basic operations in place. Accordingly, I will propose you now another derivation, which is the one that obeys purely the standard probability manipulations. To conclude this part of the derivation, which I forgot, we left behind our normalizer eta, which we said it's a number. Remember what is the meaning of a normalizer in a conditioning. The meaning of the normalizer is to shift the distribution over all possible, in this case, states in a way that it sums up to 1. And so we could easily obtain that normalizer by summing up all the possible values of the numerator evaluated at all possible state x of t. So basically we calculate for each possible state this formula, we sum them up, sum these values up, and we have the inverse of the normalizer. Okay. Now, the alternative formulation that we will use for the derivation of all remaining filters, which is the Kalman and the particle, relies on, as I said, a different view. So imagine your Bayesian network, which is evolving, and at a certain point in time, you end up that you know, because we said that we can carry on filtering in an incremental fashion, you know the distribution, the estimate of the distribution of the states at time t minus 1. And then at a sudden point, the control ut minus 1 becomes available. Ut minus 1, you can regard the ut minus 1 either as a variable or as a perfect value, depending on your on your assumptions in the system. If you look at this Bayesian network over here, and I tell you, you know this, and you want to estimate this. Basically, you want to shift all the knowledge between these two values to this value over here. Well, it comes in quite straightforwardly that the action you have to take is basically use the chain rule, because you construct basically a joint distribution over the previous controls and the previous belief that you have, and you apply the chain rule between the transition model and this joint distribution. If we want to picture basically the ingredients and the process, you can remember this meaning of this graphical meaning of what it means marginalizing, which is collapsing, what it means conditioning, which means slicing, what it means chain rule, which basically can be expressed by the multiplication of two probability tables. Okay. If you want to picture the ingredients, you have a transition model that we can visualize as if it was a cube. A cube, which where each, in this case, a cube because we have three basically variables in this formula. So each variable takes one dimension, and the distribution is on xt, which means that along this axis, along each of these axes, each column of the cube sums up to 1. And then we have xt minus 1, and ut minus 1 that act as indices, basically, that help us selecting what is the distribution of next possible states. Let's assume that this is my previous state and this is my previous control. Then the distribution over the possible states will be the vertical slice, basically, which I index by knowing u and x. This is one of the ingredients. Then we have the prior belief that I will write here as p of xt minus 1 given whatever we know before. And we can picture it as if it was just a bar, like a histogram. And then we have the control, u of t, okay? Which is, in this case, we assume it known. If it would be a probability distribution, then we would represent the control as another, basically, bar, another histogram over the possible controls. Now, assuming that the control is a perfect variable, we could basically conduct this operation of determining the next state, x of t, from the previous state and the previous control, just by going into this table over here and selecting the slice that corresponds to the known control. What is this slice? This slice, you can see it, you can picture it as if it was a matrix where each column is a possible distribution over the successor states after having executed the known command ut minus 1, right? Each of these columns sums up to 1. And on the columns, basically, so on this axis over here, we have the previous states, which acts as a selector of the particular distribution. And then, basically, by multiplying this table and this table over here, which means technically performing a marginalization, okay, we can determine the marginalization, the chain rule. We can determine, with the chain rule, you get a joint distribution. We could get the joint distribution between xt and xt minus 1 given ut minus 1. Okay, so just to visualize, let's assume that you have this state here, which is very likely, and this state here, which is very likely. What happens once you do the chain rule between this distribution and this conditional table? Well, you will have that this column over here gets magnified because, not magnified, but gets a high value, so to say. This column here, the second one, we said that here we have not much probability, then it gets lessened. This one here, I think, was the one with high value, so it will be enhanced, and others will be basically punished. We said that we have here and here high value and low value all over the rest. So we'll have a high stripe here and another stripe here. Okay, assuming that we know perfectly the state, so that we have probability mass 1 and 0, 0, 0, 0, then we will basically select straight away one of the columns of this conditional probability density. Anyway, all what we have done in order to shift basically our knowledge between this and this into this variable over here was doing a chain rule, which will return then a joint distribution over these two, and then after that we will do what we do normally to kick away a variable and marginalization. Now if you want to see it this way, basically we perform a chain rule over here to determine the joint distribution between the current and previous state. And after we have the joint distribution between these two variables, what do you do in a joint distribution once you want to remove a variable? Well, you do marginalization. Now, the summation here are written just to help you thinking to visualize the process. But actually, in general, we could just call this action of suppressing a variable by collapsing all the knowledge of the other variables onto this plane as marginalization. If we want to express this equation programmatically, we have this fragment of program that tells you what happens. Basically, it tells you that the probability with xj, we denote the leading state, so the state where we arrive, and with xi, we denote the starting state, the value of the starting state. And basically, this equation here says that in order to figure out how likely it is to end up in the state xj, you have to consider the probability you had of being in the state xi at time t-1, and then you have to consider the probability of ending up to the state xj, starting from the state xi, given the control u. This gives you a contribution, and then this will be one possible way you reach the state xj. And then let's assume that there is another possible state in the previous value of the state in the previous set that will highly likely bring you to the same xj. Well, what you will find is that this predicted belief will receive basically two big contributions from these two states through the transition model. Of course, each contribution of the previous transition has to be weighted by the actual probability of staying in a state with high likelihood in the previous time, right? Because assuming that you have a transition model that tells you that with probability 1, if you are in state 1, you will end up in state 2, right? So probability 1, given any control. But it might also be that at in your running estimate, you are in state 1 with probability 0. So the way you will never have a chance to execute that transition. And so the predicted belief will not, of being in state 2, will not receive any contribution which is, would arise from performing the transition from the state 1. Because you didn't have any chance to be in the state 1. Now, basically what we have done is to collapse all this information and then to shift it towards the actual time x of t, right? All the previous information. But there's one aspect that we did not yet consider. And which aspect aspect is this? Well, this aspect is the measurement, right? So if you have a measurement, like what we computed before is just the probability of moving to a state, but we didn't open yet our eyes, right? Imagine that you are walking with with closed eyes, no? And then you issue control to your legs will move, but until you don't open your eyes, you have an estimate of your position, which is quite brittle. Now, might I tell you, if I ask you, did you move 1 meter or 1 meter and 3 centimeters, you might not even know it, right? You might guess that you didn't move 10 meters, right? In order to refine, let's say this way, your state, you need to incorporate the observation. So you open your eyes, and then you can see maybe that the wall is at 3 millimeters from your face. You say, oh, maybe I moved 1 meter and 10 centimeters, right? More or less. So what we want to do at this point is to integrate the measurement that then becomes available. So measurement is a value that enters in our filtering mechanism. And how do? We focus on this tiny little Bayesian network, which is consisting of just 2 nodes, and we paint xt in pink, zt in bluish, and then we do the inference. Now you have this, you have a conditional distribution of zt given xt. You have the conditioning distribution p of xt given all the rest that you have computed at the time before. And what you can do is simply compute the joint distribution and then over z and x and then marginalize. And this is exactly what we will be doing. We can compute the joint distribution over z and x by multiplying the probability of x times the probability of x given z given x. And then this gives us basically a 2-dimensional table, if you want to think about a table. And then we have 2 variables, of which one, we don't know what to do with this one. And so we can condition actually on the actual measurement. Remember that this gives us a distribution. And then in order to eliminate, this is still a random variable, in order to eliminate this random variable, we have 2 ways. One is marginalization, but we don't want to do it because we know the value. You do marginalization when you don't know the value at all. Or we can just do conditioning, and given that we know the value, it's much more sensible to do conditioning. And we end up with this equation over here. Now, in the discrete case, you observe that computing this joint distribution, this joint table, is quite useless, because in the conditioning action, you will be only considering the row that corresponds to the actual measurement z that you have done, right? So you could easily ignore all the other rows of the table. This is also in the discrete case. And then you can just like focus on the row of the table that corresponds to the actual measurement that you had done. I see the door, let's say. It's useless that you think if you don't see the door because your sensors say that you see the door. And so if we implement this simplistic thing, we could just write that to you alter the probability of each possible state by considering its probability before the integrating the measurement, and you multiply this probability by the actual probability of performing that measurement given the particular state, xi. Remember that this b is just a vector in our discrete world. It's just a vector that was indices corresponds to state. So xi is just an integer in this case. And then on the fly, you can easily compute the normalizer, and at the end, you can multiply, you can divide the belief, the entire vector by the normalizer, and you have the distribution after the condition. Okay? So we identified 2 steps in filtering. One, which is the predict, right? Which basically consists in performing an open loop motion, an open loop transition of our system, open loop from the point of view of observation. So we just move blindly to the next state, and we can perform predict basically by applying the chain rule to the previous belief and between the previous belief and the transition model. in order to obtain the joint distribution, and then after we have a joint distribution between the current and previous state, we can marginalize out the previous state. Okay, this is the most basically generic manner. And then at the end of this process, we have the probability of being in a state but not having yet opened our eyes. Then the other component is the so-called update. We had figured out that we could carry on the update, just which consists of integrating the measurement. And the measurement integration can be done by knowing the previous state, let's say in open loop, by knowing the measurement, and by knowing the measurement model. We can compute the joint distribution between the belief and the observation model. We can compute the joint distribution between the states and the measurements, and then we can condition on actually the measurement that the actual value of the measurement that we know in order to pick up the slice of the distribution which is interesting for us, which is then consistent with a specific measurement. Okay? And this basically concludes our very quick recap on filtering. Let's see. The stream seems to be in good condition. I hope that this fixes the suboptimal video that we had during the lesson. But now with this fantastic microphone, I think we will not have issues anymore. So, bye-bye.